So as we embark on electrochemistry, we should take some time to review oxidation numbers and then explore what it means to balance redox reactions via the half reaction method. You might recall back in the fall, we talked about oxidation numbers as being either a charge or an apparent charge for atoms within compounds. The rules that we had then, we had a series of fairly goofy rules, and all of those rules were based on electronegativity. So electronegativity increases as we go to the right on the periodic table and toward the top. So things like fluorine get really high priority in terms of oxidation numbers. So I just want to review a little bit what the rules were that we had back in the fall. And the top rule, the most important rule, was that the total oxidation number needed to equal the overall charge of the molecule. Second to that was that group 1A atoms had a positive 1 charge, group 2A atoms had a positive 2 charge. Fluorine got a rule by itself, and fluorine has a negative 1 charge. Then hydrogen seems to have a positive 1 charge. Oxygen has a negative 2 charge most of the time, and groups 7A, 6A, and 5A have negative 1, negative 2, and negative 3 charges. Now, if there is a tie, or if there are two rules that apply to the same compound, then the rule with the lower number wins. In other words, the rule that has higher priority, higher up on this list. Okay, so let's apply that to some reactions, and we should remember, or we should recall, that redox reactions involve changes in these oxidation numbers or changes in oxidation. And something is always reduced and something is always oxidized. Whatever is reduced gains electrons, whatever is oxidized loses electrons. So we have a couple of reactions here. One is the combustion of methane. And if we work out all of the oxidation numbers, then we have an oxidation number of -4 for the carbon, +1 for the hydrogen. An oxidation number is 0 for the oxygen itself. In carbon dioxide, we have a +4, a -2 for the oxygen, and then the hydrogens in water are +1 and the oxygen is -2. So the carbon here goes from an oxidation number of -4 to an oxidation number of +4, meaning that each carbon loses 8 electrons and it is oxidized. The oxygen goes from an oxidation number of 0 to an oxidation number of -2, meaning that it gains 2 electrons. If we go down to the bottom, to the zinc plus copper chloride, then the zinc starts out with a 0 oxidation number and goes to a +2. So the zinc is oxidized. The copper has a +2 charge initially, +2 oxidation number, and goes to 0. So the copper is reduced. Okay. These orange circles and the red squares, as you'll recall from the fall, were a way to figure out what the oxidation numbers are based on tallying up the total oxidation number for a molecule. Okay, so let's talk for a little bit about balancing with the half reaction method. This reaction, or this method, is really good for balancing reactions that happen in aqueous solutions. And so we're going to take a stepwise approach here. We've got a 7 or an 8-step process, depending on if the solution is acidic or if it's basic. The general idea is that we're going to add things to the reaction that we think might already be in the solution. So we'll be making use of adding in water, or thinking about water contributing to the reaction, and H plus contributing to the reaction as well. And if it's in a basic solution, there should be lots of OH around, and we can add OH into the reaction as well. So the general process is that we're going to separate out the unbalanced reaction into these things called half reactions. So we're going to consider the oxidation part and the reduction part to happen separately. And this is important because this is going to set us up for electrochemistry, where the half reactions actually happen in two separate physical places, like at the cathode and the anode of a battery. So we're going to conceptually here separate them into half reactions, the oxidation and the reduction. Then we're going to start by balancing things that are not oxygen and hydrogen. Then we balance oxygen by adding H2O. We balance hydrogen by adding H+. If there is a charge imbalance on either side of the reaction, we add electrons. We multiply half reactions by small integers to make sure that the number of electrons lost is equal to the number of electrons gained. And then we combine the half reactions back together and make the overall reaction. And we can do this. This is the procedure for an acidic solution. If it's in a basic solution, then you have an additional step where you add OH to both sides and that can react with the H+. Okay, so what I want to do is take you through an example. I have one example in an acidic solution and one example in a basic solution. So the first example is iron plus the dichromate ion, giving us iron 3 plus chromium 3. And this happens in an acidic solution. Now the way that this slide works, and the way the next one works as well, is that each step in the process I have listed as a separate line, and all of the new stuff for that line is indicated in red. So our first half reaction is going to be the iron part of this. This happens to be the oxidation part. So iron is going to lose an electron. So we have iron 2 plus going to iron 3 plus. It's already balanced in terms of everything that's not hydrogen or oxygen, and there isn't any hydrogen or oxygen, so we can skip several of the steps on the previous slide, go right to balancing charge by adding an electron. If we go to the other half reaction, we start with the Cr2O7, 2 minus going to Cr3 plus. We do have to balance that with regard to the chromium. We do that by putting a 2 in here in front of the Cr3+. Next step is to balance the oxygens. You can see we have 7 oxygens on the left, so we add 7 waters. Adding 7 waters on the right overloads the products with hydrogen, so we fix that by adding 14 hydrogens to them. Once we've done that, then the charges on each side of this reaction are different. So now we have 14 plus minus 2 gives positive 12 on the left-hand side, and we have positive 6 on the right-hand side. So we have to add 6 electrons to make those charges. So now our reduction, our gaining electrons, is expecting 6 electrons, but our oxidation is only losing 1. So we need to multiply that reaction by 6 so that our lost electrons is the same amount as our gained electrons. Once we do that, we can add together and cancel things if necessary, and we end up with this overall reaction. One of the important things that we should check with redox reactions is just check to see if the overall charge is the same on the reactant side and the product side once you have it all combined. So let's go ahead and do that. So we've got positive 12 plus another 14, that gives a positive 28, minus 2, so we've got a positive 26. And on this side, we've got a positive 18, right? I'm sorry, we've got a positive, I did my math wrong, we've got positive 26, positive 24. And on this side, we've got a positive 18 plus another positive 6. Gives us a positive 24. So both sides carry a positive 24 charge, and I think that gives us confidence that it's balanced. Here's an example in a basic solution. So here we have, this is kind of a fun one, because bromine, Br2, serves as both being oxidized, so it's oxidized to form the bromate, and it's reduced then to form the bromide. So dealing with the bromide first, that is an easy half reaction to balance. We have Br2 going to 2 Br minus, and then we have to add in 2 electrons on the left-hand side to get the reaction to balance. Since we have bromine going active in both the oxidation and the reduction half reactions, we just write it twice, and then we'll combine it at the end. Okay, so for the oxidation part, we have bromine going to two bromates. We have to have two of them to balance out the bromine. Then we add in 6 waters to balance out the oxygens. Putting 6 waters in requires us to put in 12 H plus on the other side to balance out the hydrogens. And that requires us then to put in 10 electrons so that our charge balances out between the left-hand side of this reaction. And so we have 10 electrons that are being lost. We are anticipating 2 electrons to be gained. So we need to multiply this reaction by 5 in order to have the gained electrons and the lost electrons match each other. Whoa, did not mean to do that. So now we can combine these. So when we combine these, we get this equation. And since it's in a basic solution, we have a little bit more work to do. All right, here's how you handle basic solutions. You can see that we have 12H plus here. In a basic solution, we're not likely to have 12H plus around. So we convert it into, or we acknowledge that in a basic solution by adding in 12 OHs. Now we don't want to change the reaction, so we put 12 OHs on both sides. Okay, so we add 12 OH to the reactants, we add 12 OH to the products. The number is 12 because we had 12 H plus here. This 12 H plus and the 12 OH on the same side of the reaction, we can combine those to make 12 waters. Now in this case, the 12 waters that those make will cancel out with 6 waters on the other side of the reaction. So when we tally everything together then, doing that canceling, we get 12 OH plus 6 bromines giving 2 bromates, 6 waters, and 10 bromine. And that is it. So that's how you handle acidic solutions, how you handle basic solutions. Thank you very much.